Welcome back everyone. In this section we will learn about reactions of alcohols. Alcohols react with alkali metals and some other active alkaline earth metals such as magnesium to liberate hydrogen gas, and it also forms metal alkoxide. This kind of reaction is an example of a redox reaction. For example, the reaction between methanol and sodium metal is given here. The products are sodium methoxide and hydrogen gas. In this reaction, the metal will lose an electron to form the metal cation. So because this is a loss of electrons, so metal gets oxidized. At the same time, alcohol supplies the hydrogen. So hydrogen is supplied as H positive ion, which gains the electron and forms hydrogen gas. So hydrogen is reduced. The alkoxide anion formed in this reaction are somewhat stronger bases than hydroxide ions, and metal salts of these alkoxide ions are used as strong bases in organic reactions where a strong base is needed. Most commonly used alkoxide ions in organic reactions requiring bases are sodium methoxide, sodium ethoxide, and sodium tertiary butoxide. Alcohols can also be converted to metal alkoxide by the reaction with bases stronger than alkoxide ion. For example, sodium hydride or sodium amide are strong bases which are capable of converting alcohols such as ethanol into sodium alkoxide ion. As I mentioned in the beginning of this chapter, that alcohols are one of the most versatile organic compounds. They can be converted into other categories of organic compounds. For example, reaction of alcohols with the halogen acids will convert them into haloalkanes. Tertiary alcohols react very rapidly with any of these three halogen acids. For example, if we react tertiary butyl alcohol with HCl, this reaction can be done at room temperature, and the resulting product will be 2-chloro-2-methyl propane and water. The haloalkane produced in this reaction is water insoluble, and we will see two separate layers. One would be the aqueous layer, and the haloalkane product will form another layer apart from the water layer. Low molecular weight primary and secondary alcohols are unreactive under these conditions. Primary and secondary alcohols require elevated temperatures, and they react with concentrated HBr and HI to form alkyl bromides and alkyl iodides. Primary alcohols do not generally react with hydrochloric acid. So for example, 1-butanol, which is a primary alcohol, will react with the concentrated HBr at elevated temperature. So we have to reflux it. Refluxing means temperature close to the boiling point. And the product, of course, will be a primary haloalkane. In this case, it will be 1-bromobutane. Both alcohol and HBr are water soluble or polar, so this reaction can be carried out in in a polar solvent such as water. The reaction of secondary alcohols with HBr and HI will generally give some rearrangement product, which is an evidence for the formation of a carbocation intermediate during the reaction. For example, if we react a secondary alcohol such as 3-pentanol with HBr, we will get a normal substituted product, that is a 3-bromopentane. However, there will be one additional product, which is 2-bromopentane. This 2-bromopentane is a product of rearrangement. This rearrangement takes place when the intermediate carbocation undergoes 1-2 proton shift, and of course there will be water as a product also. In case we have a primary alcohol with extensive beta branching, it will give large amount of rearranged product. For example, the reaction of 2,2-dimethyl-1-propanol, which has 2 methyl group at beta position. So this is our alpha carbon and beta carbon. So now in this case, we have extensive branching at beta position, and our alcohol is a primary alcohol. This alcohol reacts with HBr to give mostly the rearranged product. This rearranged product is obtained by 1,2 methyl shift during the reaction mechanism step. The reactions of various kinds of alcohols with halogen acid show that tertiary alcohols are most reactive, whereas primary are least reactive. So this relative ease of reactions of alcohol with halogen acid, and also the presence of rearrangements during these reactions, indicate that the reaction takes place via Sn1 mechanism. We know that in Sn1 mechanism, a carbocation intermediate is formed, and the rearrangements of primary carbocation to secondary or tertiary carbocation is quite common in Sn1 mechanism. So based on these evidences, we or chemists propose that the reaction of secondary and tertiary alcohols with halogen acids occur by Sn1 mechanism. Let's write the mechanism of reaction of secondary and tertiary alcohols with halogen acids. As established in previous slide, this reaction takes place via Sn1 mechanism. Normally, in Sn1 reaction mechanism, the first step involves loss of leaving group. And this step should result in formation of a carbocation. If our alcohol is a tertiary alcohol, then our carbocation will also be a tertiary carbocation. However, hydroxyl group is a bad leaving group. So therefore, hydroxyl group does not leave by itself. So in order to make this bad leaving group a better leaving group, we add small quantity of acid. Fortunately, this reaction is already taking place in presence of acid, so therefore the reagent, which is the acid, will act as a catalyst also. So the first step will be a proton transfer step, in which the hydroxyl group will grab a proton from an acid and this transfer of proton will result in formation of a positively charged oxygen cation, in which the leaving group is a water molecule. Now water is an extremely good leaving group. So once we have a water as a leaving group, then the leaving group will leave, which is the loss of water molecule, and this step 2 will generate a carbocation intermediate. Now this step is the rate determining step. And we know that tertiary carbocation is the most stable kind of carbocation. And this step is the slow and rate determining step. The first step, in which the proton was transferred to the hydroxyl group, is also a reversible step, but it is a rapid reversible step. So therefore, the proton transfer step is not the rate determining step. The second step in this case, in which carbocation is generated, is the slow and rate determining step. The final step involves the bond formation between the carbocation, which was generated in previous step, and our nucleophile, and nucleophile is supplied by the halogen acid. And this step is a fast step, so therefore this step does not contribute towards the rate of the reaction, and the product will be a haloalkane. The reaction of primary alcohols with halogen acids proceed by Sn2 mechanism. As we have learned previously, that Sn2 mechanism involves only one step. However, because hydroxyl functional group is such a bad leaving group, in this mechanism also, the first step will be a transfer of proton to make hydroxyl group a better leaving group. So the reaction between a primary alcohol, such as 1-butanol shown here, will involve a initial step in which a proton is transferred to the hydroxyl functional group, and this proton transfer step will convert the hydroxyl functional group into a water leaving group. The hydronium ion used in this proton transfer step is generated by the reaction of water and the halogen acid. Once the hydroxyl functional group is converted into a better leaving group, the next step will involve the attack of nucleophile to generate a haloalkane. And because this is a Sn2 mechanism, the nucleophile will attack from the opposite side of the leaving group. And this step, of course, will be a slow and it will not be reversible. It will be a slow rate determining step, and this mechanism is a Sn2 kind of mechanism. And in this step, the uh, geometry is also reversed. So for example, if our starting alcohol is an S optical isomer, then the stereochemistry will flip. So the product will be R isomer. Our nucleophile, let's generalize the nucleophile. It's a halogen nucleophile. So this is the reaction mechanism in case our alcohol is primary. As we learned earlier, that primary alcohols with extensive beta branching give large amount of products derived from rearrangement. This is due to the unique mechanistic steps involved in this reaction. For such primary alcohols which have extensive beta branching, Sn1 mechanism is not possible because it is a primary alcohol, and primary alcohols, as we know, do not like to create primary carbocations. Now, because of the extensive beta branching, Sn2 mechanism is also not possible because of the steric hindrances created by the beta branching. So therefore, these alcohols react by a concerted loss of water and migration of an alkyl group from beta to alpha position. Let's try to understand the reaction of halogen acid with the primary alcohol with extensive beta branching. In these reactions, step number 1 will involve a proton transfer from the acid which will generate an oxonium ion. Oxonium ion is the water leaving group. Let's take 2,2-dimethyl 1-propanol as an example of a primary alcohol with extensive beta branching. The structure of this alcohol is shown here. As we can see that it is a primary alcohol with alpha carbon connected to the hydroxyl group and 2 methyl groups present at beta position. Now step number 1 will involve the transfer of proton from the acid, which will generate the oxonium ion, which is a better leaving group. As we understood in previous slide, that Sn2 attack is not possible because of this large bulky beta branching. So nucleophile cannot approach from the rear of alpha carbon. So therefore Sn2 attack is not possible. So in step number 2 will involve a simultaneous breaking of bond as well as a shift of methyl group from beta position. This is the beta position. So step number 2 will involve the transfer of methyl group. At the same time, the leaving group will leave. So this is a concerted step, and this will be a slow and rate determining step. And in this step, the product will be a tertiary carbocation, and water. Now, tertiary carbocations are relatively stable, so that is the driving force behind this rate determining step. The final step will be the attack of nucleophile on the tertiary carbocation, and it will generate the haloalkane. This step will be a fast step, and the product will be a rearranged haloalkane product. The reaction of alcohols with the halogen acids is a convenient method to convert alcohols to haloalkanes. An alternate method for synthesis of bromoalkanes from primary and secondary uh, alcohols is through the use of phosphorus tribromide. This reaction is known as bromination of alcohols. This method of preparation of bromoalkanes take place under milder condition than the treatment with HBr. Although rearrangement sometimes occur with the phosphorus tribromide, but the extent is considerably less than that with HBr, especially when the temperature is kept below 0 degrees Celsius. The mechanism of reaction between alcohol and phosphorus tribromide involves two steps. In step number 1, the oxygen atom of alcohol functional group will displace the bromide atom from phosphorus tribromide, resulting in the formation of a protonated dibromophosphite group. We know that hydroxyl group is a bad leaving group. However, this protonated dibromophosphite group is an excellent leaving group. The second step involves the attack of bromide nucleophile, which is generated in step number 1 on the alpha carbon atom, and the protonated dibromophosphite group leaves, and this results in formation of bromoalkane. This second step is a Sn2 kind of substitution step, and in the phosphorus dibromo product which is obtained at the end, so remaining two bromine atoms in this can be used to carry out the same uh, reaction step. So hence 1 mole of phosphorus tribromide will react 3 times, and it will convert 3 moles of, or 3 molecules of an alcohol into bromo alkane, and at the end the phosphorus tribromide will convert into phosphoric acid. The reaction of primary and secondary alcohol with the thionyl chloride gives an alternate method of chlorination of alcohols. In this reaction, high yield of chloroalkanes are obtained, and rearrangements are rarely observed. So therefore, this method is widely used when alcohols are needed to be converted into chloroalkanes. The reaction between 1-heptanol, which is a primary alcohol, and thionyl chloride is shown here. The product of this reaction is a substitution product in which the hydroxyl group is substituted by a chloro group. One of the product in this reaction is hydrochloric acid. Therefore, this reaction is carried out in presence of a base. Most commonly, pyridine or trimethyl or triethylamines are used as a solvent. So these bases neutralize the HCl which is produced during this reaction. These amines not only neutralize the HCl, but they also catalyze the reaction by converting alcohol group to alkoxide group. For example, if we use this alcohol in the beginning, the base used, it could be either pyridine or triethylamine. It will convert the alcohol to alkoxide, and alkoxide is much better nucleophile than alcohol molecule. So these bases are essential for chlorination of alcohols using thionyl chloride. Another key feature of reaction of alcohols with thionyl chloride is that this reaction is stereoselective. Inversion of configuration will take place in this reaction. For example, if we start with the S isomer of any alcohol, then the product haloalkane will have R configuration. The mechanism of reaction between alcohols and thionyl chloride also involves two steps. Step 1 of this process involves the formation of alkyl chlorosulfide. In alkyl chlorosulfide, there is a bond between the sulfur atom and the oxygen atom of alcohols. This product is known as alkyl chlorosulfide. This group in the alkyl chlorosulfide is a chlorosulfide group, and this chlorosulfide group is a good leaving group. The hydroxyl group is a bad leaving group, so therefore the first step of this reaction mechanism is the conversion of bad leaving group to good leaving group. The step number 2 involves the nucleophilic displacement of chlorosulfide uh, group, which is a good leaving group, by chloride nucleophile, and it will result in formation of the chlorosubstituted product. So this step is similar to Sn2 mechanism, and it proceeds by the backside attack by nucleophile, and the leaving group leaves, and that's why the stereochemistry gets inverted in this reaction. The the chloride ion also leaves. Excuse me. The sulfite group rearranges to form sulfur dioxide, and a chloride ion. In last reaction, we saw alcohols readily react with thionyl chloride to form alkyl chlorosulfides. Alcohols also react with a compound called sulfonyl chloride to form alkyl sulfonates. The structure of sulfonyl chloride is similar to thionyl chloride, and in thionyl chloride, the oxygen atom of a hydroxyl group forms a bond with sulfur by displacing a chloride ion connected to the sulfur. Similar process will take place here. So if we have a general alcohol such as ROH, let's say R prime OH, and if it combines with a sulfonyl chloride, a displacement of Cl and hydrogen will take place, and the oxygen will form a link or form a bond with the sulfur atom, and hence the resulting alkyl sulfonate will have a structure where there is a connection between the oxygen of alcohol and the sulfur atom of sulfonyl chloride. This product is known as alkyl sulfonate. The sulfonyl chlorides are derived from sulfonic acids. Sulfonic acids are extremely strong acids, and their strength is similar to sulfuric acid. Because sulfonic acid is a strong acid, hence its conjugate base, which is a sulfonate anion, is a weak base. It is also very stable anion because of extensive uh, resonance which can stabilize this anion. So it will have three contributing resonating structures. I'm not going to draw the third one, but you understand that because of these extensive resonating contributing structures, this anion is extremely stable. Hence, a sulfonate anion is an excellent leaving group. The most commonly used sulfonyl chloride is Paratolvin sulfonyl chloride. We have not learned aromatic hydrocarbons yet, so therefore I'm going to tell you that benzene ring with a methyl group connected to it is known as toluene, and para position is the position opposite to the substituent, so this position will be known as para position. So paratolvin sulfonyl chloride means that we have a toluene. This is toluene, and at para position we have sulfonyl chloride group connected to it. So that's why the name paratoluene sulfonyl chloride. So this sulfonyl chloride is commonly used to react with alcohols to form ethyl paratoluene sulfonate. This group which is formed after this substitution step is known as tosylate. Therefore, this whole compound is also known as ethyl tosylate because ethyl group is connected to a tosylate group. Pyridine is added to catalyze this reaction and also to neutralize the HCl which is produced as a product in this reaction. Tolvin sulfonyl chloride is also abbreviated as TSCl, and it is also sometimes known as tosyl chloride. Another commonly used sulfonyl chloride is methyl sulfonyl chloride, which is also known as methyl chloride. When alcohols react with methane sulfonyl chloride, the resulting product will be alkyl methane sulfonate, which is also known as mesylate. So for example, in this case, we are reacting cyclohexanol with methane sulfonyl chloride or mesyl chloride. So therefore, our product is cyclohexyl methane sulfonate, also known as cyclohexyl mesylate. So therefore, this group is known as mesylate. Now you may be wondering that why we are studying the reaction between alcohols and the sulfonyl chloride. The answer is that product of both of these reactions involve a sulfonyl chloride products such as tosylate or mesylate, which are extremely weak bases and a stable anion in both cases, in tosylate as well as mesylate. Because of these two properties, both tosylate and mesylate are excellent leaving group, extremely good leaving group. Hence, whenever we want to react alcohols in which the OH group needs replacement or substitution, the first step will be conversion of this OH group to a better leaving group. In previous reactions, we reacted with alcohol, we reacted OH group with acids to convert OH group to water leaving group. which was one option. Now, mesylate and tosylate gave us another option of converting the OH into a better leaving group. Another key feature of these two reactions is that in formation of either a tosylate or mesylate, the reaction involves breaking the OH bond, not the carbon oxygen bond. So this carbon oxygen bond does not break. Only the oxygen and hydrogen bond breaks. So therefore, it does not affect the carbon and oxygen bond. If the carbon bearing the hydroxyl group is a chiral center, if this is a chiral center, which is not in this case, but however, imagine if it is a chiral center, this sulfonate or this tosylate or mesylate product will retain the stereochemistry because nothing happened to this bond. So conversion of hydroxyl group to either mesylate or tosylate will preserve the stereochemistry of the carbon atom where hydroxyl group is connected. So therefore, hydroxyl group can be converted easily to either tosylate or mesylate while preserving its stereocenter or stereochemistry, and both tosylate and mesylate, being a good leaving group, can readily be substituted by any other nucleophile, giving us a nucleophilic substitution reaction. So in conclusion, we can say that sulfonate anions are very weak bases, and hence they are extremely good leaving group for Sn2 reactions. So therefore, conversion of an alcohol to a sulfonate ester converts the hydroxyl group, which is a poor leaving group, into sulfonic ester, which is a good leaving group. Let's take a look at a reaction in which we will see the advantage of tosyl chloride or mesyl chloride in process of conversion of 2-octanol to 2-octyl acetate. So what we are trying to achieve here is we have an alcohol, 2-octanol, and we would like to substitute the hydroxyl group with an ester group. So this looks like a simple substitution reaction. However, the OH group is a poor leaving group. So therefore, if we simply react with this acetate nucleophile, the direct Sn2 reaction will not take place. So only way to accomplish this reaction is to convert the hydroxyl group, the OH group, into something better leaving group. And tosyl chloride gives us that option to convert the hydroxyl group into a better leaving group, which is a tosylate. Remember, paratolvin sulfonate ester is also known as tosylate. Just to review again, the entire formula of paratolvin sulfonate group. So this entire group is also known as tosylate, and this tosylate is abbreviated as TS. So we don't need to write this entire big bulky group all the time during the reaction. So step number 1 is formation of this tosylate from alcohol. So starting with our 2-octanol, and it reacts with tosyl chloride, and it will result in formation of paratolvin sulfonate ester. So this step preserves the stereochemistry. So remember, this TS group shown here is this bulky group. I do not need to write this whole bulky group multiple times, so we can just write TS. The second step is the nucleophilic substitution, in which a nucleophile displaces the tosylate group, and tosylate group being an excellent leaving group, it readily leaves and completes the nucleophilic substitution reaction. This reaction takes place in presence of uh, ethanol. Ethanol is a solvent in this reaction. Alcohols can be converted into an alkene by the process of dehydration of alcohols. This process is catalyzed by acids, and it is a type of beta elimination reaction. For example, if we have 2-propanol and we conduct the beta elimination reaction, then the product of this reaction will be propene and water. So essentially what happened here is that the OH group and a hydrogen atom from the neighboring carbon, they are eliminated as water, because water is removed in this reactions. Hence this reaction is known as dehydration reaction. Examples of various dehydration reactions are shown here. As you can see that this reaction requires elevated temperature, especially in case of primary alcohols. Primary alcohols must be heated at high temperatures in presence of strong acids such as sulfuric acid or phosphoric acid. Secondary alcohols also undergo dehydration reaction, but the temperature requirement is slightly better, so they can undergo dehydration process at relatively lower temperatures. Tertiary alcohols often require temperature at or slightly above room temperature. For example, tertiary butyl alcohol can undergo this elimination reaction at 50 degrees Celsius to produce isobutylene. Let's consider the dehydration of 2-butanol. In this case, the hydroxyl group is connected to the alpha carbon, and there are two possible beta positions, and both of these beta positions do have hydrogen atoms. So when the dehydration of 2-butanol is carried out in presence of a uh, concentrated acid such as sulfuric acid or phosphoric acid, it is possible that we obtain two products. In one case, the hydroxyl group and the hydrogen from the first beta position, or beta 1, let's call this beta 1, are removed, and our product will be 1-butene. The other possibility is that the hydroxyl group and the hydrogen from beta 2 position is removed. In that case, 2-butene will be the product. So where two isomeric alkenes are possible, the alkene having greater number of substituent on the double bond will predominate. So in other words, the more substituted alkene, which is also known as Zaitsev rule, will be the major product. Hence, 2-butene will be the major elimination product in this case. Dehydration of primary and secondary alcohols is often accompanied by rearrangement. For example, consider the dehydration of 3,3-dimethyl 2-butanol. In this alcohol, the OH group is located at number 2 position, so that will be its alpha position. This alpha position has two relative beta positions. Let's call this beta 1 and the other one is beta 2. Beta 1 position does have hydrogen atoms. In fact, it has 3 hydrogen atoms. So elimination of OH group and hydrogen atom from the beta 1 position should give us an alkene. However, the product of this elimination should be an alkene where there is a double bond between number 1 and number 2 position. However, this product is not obtained at all when this reaction is actually carried out in the lab. The actual alkenes which are obtained do not resemble the elimination product which we expect. The beta 2 position does not have any hydrogen, so we do not expect any elimination to take place at beta 2 position. So only way to explain the actual product obtained in this reaction is by considering the rearrangement during the mechanistic steps. We will learn about the mechanism of this reaction in coming slides. But remember that in case of dehydration of primary and secondary alcohols, the products are obtained by rearrangements also. Acid catalyzed dehydration of 1-butanol gives us a mixture of 3 alkenes, and the major product is the most stable trans 2-butene because this is the more substituted alkene. Based on the relative rates of dehydration of alcohols and the prevalence of rearrangement during these dehydration reactions, chemists have proposed 3-step mechanism for dehydration of secondary and tertiary alcohols. The presence of rearrangements can be explained if a carbocation intermediate is formed during the rate determining step. Thus, it can be concluded that mechanism involves a formation of carbocation intermediate in the rate determining step, and hence this mechanism is classified as E1 mechanism. The first step of mechanism of dehydration reaction of alcohols involve a proton transfer. This proton transfer step converts the bad leaving group, that is hydroxyl group, into a good leaving group, which is oxonium ion. For example, consider dehydration of 2-butanol. So first step of this reaction will involve a transfer of proton from hydronium ion. Hydronium ion will be generated by the reaction of acid and water. As we know, the hydroxyl group is a bad leaving group, and after a proton is transferred from the hydronium ion to the hydroxyl group, we will get a positively charged oxonium ion, which is an extremely good leaving group. This step is a rapid and reversible step. Hence, it is not a rate determining step. The second step of this dehydration reaction mechanism will involve the cleavage of bond between carbon and oxygen. That is, the leaving group leaves as water and it results in formation of a carbocation. This step is a slow step and hence it is a rate determining step. Because 2-butanol is a secondary alcohol, hence the carbocation formed in this step is also a secondary carbocation. In the third and final step, a proton transfer to water molecule from a carbon atom which is adjacent to the positively charged carbon. After this proton transfer, the sigma electrons of the carbon and hydrogen bonds become pi electrons and they form a carbon-carbon double bond. And this step is also a fast and reversible step, and it will generate an alkene. Both cis and trans alkene will be obtained. Dehydration of primary alcohols with the little beta branching gave terminal alkenes and rearranged alkenes. For example, dehydration of 1-butanol gives a mixture of 3 alkenes. You get trans 2-butene, cis 2-butene, and a terminal alkene, that is 1-butene. The mechanism of this dehydration reaction of primary alcohols also involves multiple steps. In step number 1, a proton transfer from an acid to hydroxyl group will take place, which will convert the bad leaving group, that is the hydroxyl group, into a good leaving group. This step is fast, therefore it is not rate determining step. In step number 2, a proton from the carbon next to the oxonium ion is transferred to water, and simultaneously the leaving group leaves. And this results in formation of terminal alkene, that is 1-butene. This mechanism step is in E2 elimination reaction mechanism, and this explains the formation of one of the product, which is 1-butene. The formation of other two products, that is trans-2 butene and cis-2 butene, are explained by the rearrangement step, which takes place during the proton transfer step from the beta carbon. The mechanism of formation of other two products is explained in next slide. Let's try to understand the mechanism step, which results in formation of cis-2 butene and trans-2 butene. After the proton transfer step, which results in conversion of a hydroxyl group to oxonium ion and hence making it a better leaving group, a 1,2 proton shift takes place as shown here in this mechanism step. This is the oxonium ion which was formed in step number 1, and there are 2 hydrogen atoms present at this beta position. A proton transfer step takes place simultaneously as the leaving group leaves. So this results in formation of a carbocation. So this is a 1,2 proton shift. So proton from this beta carbon shifts to the alpha carbon where the oxonium ion or the leaving group is leaving. So this will result in formation of a carbocation where positive charge is present on carbon number 2. Once this carbocation is formed, a proton transfer from the carbon atom next to the positive charge will result in formation of cis and trans-2 butene products. This proton is transferred to water, and the sigma bond between carbon and hydrogen shifts to the to form a pi bond, and this results in formation of alkenes as product. This mechanism step is an E1 mechanism. As with the other elimination reactions, the major product is the more stable alkene, so therefore the trans alkene will be the major product and the cis alkene will be the minor product. Dehydration of alcohols with extensive beta branching will always involve carbocation rearrangement. For example, in case of 3,3-dimethyl 2-butanol, after the leaving group leaves, of course, in this case, the hydroxyl group will first convert into a better leaving group, but after it leaves, it will result in formation of a secondary carbocation. As we know that secondary carbocations are less stable than tertiary, hence a methyl group from the beta position will undergo 1,2-methyl shift, and secondary carbocation will convert into a tertiary carbocation intermediate. The reason is that tertiary carbocations are more stable. After a tertiary carbocation is formed, usual elimination step will take place. There are two different neighboring beta positions, so let's call this beta 1 and beta 2, and elimination from beta 1 position will result in formation of 2,3-dimethyl 1-butene, and elimination from beta 2 position highlighted in this yellow will result in formation of 2,3-dimethyl 2-butene. Earlier in chapter number 6, we learned about addition reactions of alkenes. And in that chapter, we learned that alkenes undergo addition reactions with water in presence of an acidic catalyst to form an alcohol. In today's chapter, we learned that alcohols also react with acids, or in fact, alcohols also undergo acid catalyzed reaction in which they form an alkene. So therefore, we can say that this reaction is a reversible reaction. Alkenes react with water to give addition reaction and the product is alcohol. At the same time, alcohols in presence of acid will give us back alkenes. So acid catalyzed alcohol dehydration and alkene hydration are competing processes. The presence of water can shift the equilibrium to the right side. If we have more water, that will shift the equilibrium to the right side, that is, it will favor the formation of an alcohol. More water means dilute acid. So therefore, if we conduct this reaction in presence of a dilute acid means more water means equilibrium will shift to the right, so hence addition reaction will take place. So dilute acid favors addition reaction in which alcohol will be the product. However, if we conduct this reaction under such conditions that water is removed, then it will favor formation of alkenes. So a removal of water favors dehydration. That's why dehydration reactions are carried out in presence of strong acid. Strong acid means less water, and also high temperature above 100 degrees Celsius. So at that high temperature, water is evaporated easily, so it is removed. So under those conditions, dehydration is preferred. So equilibrium shift to the left hand side, which results in formation of an alkene. This equilibrium between hydration and dehydration processes illustrate a very important principle in the study of reaction mechanism, and this principle is known as principle of microscopic reversibility. According to this principle, the sequence of transition states and reactive intermediates for any reversible reactions must be the same but in reverse order for the backward reaction as for the forward reaction. An illustration of this principle of microscopic reversibility, you will notice that the mechanism which we have learned in today's chapter, in which uh, acid catalyzed dehydration of 2-butanol gave 2-butene, is exactly reverse of that presented in chapter number 6 for acid catalyzed hydration of 2-butene to 2-butanol.